Hello, my name is Frank McKenna. I'm here at UC Berkeley working for the Near East Sim Center. This is a short video on abstraction and object-oriented programming within C++. The purpose of abstraction is to reduce complexity by removing unnecessary information. As programmers, we really don't care or want to know that the hardware is dealing with zeros and ones. We're quite happy working with the abstractions, the floats, integers, doubles, and characters that the programs provide. Yesterday we were even happier because we now get to deal with we bring our own abstractions into the language. We can deal with points, nodes, and elements. So abstraction has simplified many aspects of computing, and it makes it possible to build complex systems. We would not be where we are today if all programmers were still writing code in zeros and ones. Now, it's computing languages that provide programmers the ability to create these abstractions, and the higher level language provide more capabilities, albeit at the expense of performance, than lower level languages. Today we're looking at C++, which is a higher level language to C. Abstractions we came up for a finite element method. We had these nodes, loads, elements, and constraints. We had some container object, a domain. We have matrix and vector so that the elements can do their computations. We have an analysis object, which performs the analysis. And then we looked yesterday at the elements. Could we define now elements so that we could mix elements, have different types of elements, trusses, beams, shells within one finite element program? And we brought up the solution that we'd be using structs. We'd have our elements data type. Within the struct, we'd have unique things for each type of elements, parameters, history variables, and nodes. And the thing that made it work was this concept of this element state function, which was really a function pointer. Now, when we created a new element type, we just provided with the correct function pointer depending on what type of element we were actually using, whether it was a beam or a truss or a shell. They each have different function pointers that we'd create this. So what we're really doing is starting to hold both the data and pointers to functions that work on the data within the same object. We are actually beginning to program in an object-oriented paradigm within C. So we mentioned on the first day that the approach for building a large system was to continually divide it into tasks. These tasks turned out to be our functions, and then we start worrying about how the data is passed between functions. In the object-oriented design world, it's a different approach. Basically, we look at our world and we identify the objects that are going to be in our world, and then we figure out what is the interaction between the objects. Now, it's kind of difficult, as we've seen, to program in an object-oriented programming paradigm within C. Tying the data and the object functions together is a bit of a chore. The solution is to start using C++. It makes it a lot easier to do this object-oriented paradigm. Now, the C++ language, the details, it was developed again at Bell Labs in 1979. If you remember, that's where also C came out of. It was originally called C with classes, but it was renamed to C++ in 1983. It's a general purpose language. It provides both procedural and object-oriented features. You can mix and match the two programming styles. It is an incremental upgrade to C. Now, the updates to C++ provide C with object-oriented capabilities. The features of object-oriented capabilities are encapsulation, inheritance, and polymorphism. I'll talk about this in the next two slides. We also get a standard template library, which allows the programmer to choose from a number of built-in data structures. Remember, the data structures are those things for managing collections of objects. They give us access to the object, storage of the object. And then C++ provides additional features to make C programming easier. Rephrase that as fixing some of the problems that were seen as in the existing C programming language. So what is encapsulation? In an object-oriented world, the data and the functions are bundled together inside a single class. The class provides this interface to the outside world. Think of it like an egg. The world only sees what's on the outside of the egg. They really don't know what's on the inside of the egg. The inside of the egg, that's our data that's hidden from the user. And also what's hidden from the user is how those methods are implemented. What this allows, and why this is so powerful, is that the programmer can come along later, change the data, change how the methods are implemented, and that does not affect anybody who's been looking at the egg. so any other class in the program is not affected if the developer of the original class decides to come along and change how his class works. As long as he keeps the same method, it does not break any existing code. That's why encapsulation is such a powerful feature. Other things, so let's talk about inheritance and polymorphism. Polymorphism is the ability to treat objects of different types in a similar manner. For example, an analysis object in a finite element program would loop over all elements, asking them for their tangent matrix. The analysis object, it does not care what type of element it is, all it wants is a tangent. It doesn't care if it's a beam, a truss, or a shell. The ability to treat all of these type of objects as the same is what polymorphism is. Now, inheritance occurs when one class derives the methods and data of a parent class. In this example, beam, trusses, and shells, these are deriving the methods and data of a parent class. The methods and data they're deriving, for example, are the tag and the ID. Now, the subclass is able to overwrite some of the methods that it inherits. For example, the truss, shell, and beam are all overriding the print, residual, and tangent. And this ability to override the parent class's method, this is what enables polymorphism. Now quickly some terminology I'll be using throughout. So the element is considered the parent class. The truss, beam, and shells are called child classes or subclasses of the element class. Truss, beam, and shell are also derived from element. Truss, beam, and shell override the methods tang, print, and resid of the element. They inherit the tag and ID method. And when I refer to a class, I'm referring to the actual implementation. When the program is actually running, it's actually objects that are created of a specific class type.